Yes, thanks a lot again to the organizers for inviting me. I'm really sorry I couldn't not come, and I'm grateful also for the opportunity of giving this talk online, and at least I could listen to Andrea's talk, which was also the perfect introduction for my talk. I will also discuss cavity-mediated interactions in like non-stationary states, but in ground states, let's say, or like equilibrium state, and not for bosons, but for fermionic matter. So let me go to the outline. Let's say doesn't work. So first of all, I would like to introduce the models and the system where we realize this cavity-mediated interaction between fermions, and then I will split the first part will deal with the static part of the cavity-mediated interaction, which is already peculiar and aligns with the topic of this workshop, because it is a very long range, actually naturally infinite range interaction, but it is an oscillating interaction, so it has a very sharp momentum structure at finite q in terms of the transfer momentum. And this structure will allow us to solve the competition problem between different ordering phenomena exactly, let's say, and will lead to interesting forms of unconventional pairing. In the final part of the talk, I will switch gears and go to the dynamical part of the interaction, which, due to another peculiarity of the cavity-mediated interaction, exactly the fact that the cavity has a very well-defined energy, a resonance, makes the dynamical component of the interaction very important in many cases. And I will show how this can modify, yet again, the nature of the interaction and make even the role of the quantum state of light, of the mediator of the interaction, important. So 2 slides about the models. So we start by the fact that we consider how light couples to matter in the standard way, in this non-relativistic minimal coupling that everybody knows, where we have electrons here in the psi, and we have the standard vector potential. And we want to couple these photons to a Fermi surface, so we want a finite density of quantum degenerate matter, and for instance, electrons in a solid. In order to make the coupling to light, or make the light mediate an interaction, even in vacuum, we need to do something so that the quantum nature of light becomes important. So even 0 or few photons can affect the matter. And to do that, we need to confine the light, which is done typically using cavities. And if you do it, for instance, putting a solid inside a cavity, you get a coupling between photons, which have modes enabled by Q, to the electron current, which is, if you want, the lattice version of this minimal coupling P dot A. And the electron current is defined this way. And this realizes really a new regime, if you want, of the high energy quantum electrodynamics. It moves it to low energy, finite density of matter, and potentially due to the confinement, strong coupling. There is another category of quantum matter that we can couple to cavity and therefore use cavity-mediated interaction with the Fermi surface, which are ultra-cold atoms, ultra-cold Fermi gases, again, within a cavity. And, to couple to the motional degree of atoms, many of you know that you need to use the dispersive coupling that Andreas already discussed, which couples then the same photons now to the density of the atoms. So not the current of the electrons, like in solids, but to the density of the atoms. And both are interesting and relevant. There are many ongoing experiments in both cases. Let me start for the ultra-cold atoms. We have heard in the talk of Andreas that this is quite well established, this type of coupling between light and matter for ultra-cold bosons. There are also now experiments with fermions, I guess roughly since 2020. And in solid state, there are also several experiments, and I want to make a comment that maybe you have some question about later. The fact that in solid state to reach really the quantum QED regime is more difficult, and you need typically very strong compression factors, because if you take just a volume of the cavity which has a size of the order of the wavelength of the light, then the scale of the coupling G naught is like 0.1 de Hopping, like in a solid. So it's like tendentially a small quantity, but even in this small coupling regime, it seems that the cavity can do a lot to a material. There's been an experiment very recently that showed that you can move changing critical temperatures for like transitions in a solid by like 50 or 100% just putting the solid in a vacuum of the cavity. We can discuss this, but now let me switch gears and concentrate on a particular version of actually this type of coupling to the right. And which is, let's say, we consider a single mode cavity, let's say a standing wave, which has a characteristic wave vector Q naught in this direction, like these are supposed to be the mirrors, we have the Fermi surface, and there is this Q naught in this direction. So now the single cavity mode couples with a strength G to the Q0 or Q naught component of the density defined in the standard way. Now, if you look at this is similar to like coming from solid states to the coupling between electrons and phonons rather than coupling to electrons and photons, because we couple to the density and not to the current. But there are differences like this infinite range and or if you want the fact that you couple very sharply to a single momentum component of the density. This type of coupling, which I just told you is not natural for electrons, it can be engineered also for electrons, again, using two photon transitions like has been proposed, not yet realized. And just to justify that, I will concentrate basically in all the rest of this talk on this type of coupling to the density. And it's natural for ultra-cold atoms, but I will call it general light matter coupling, with having in mind that it can also be realized in solid in a different maybe regime of parameters, but still I want to make a claim that is even more general than just ultra-cold atoms. Maybe I can stop here for a second if there are questions about model and if you can follow this part so far. Okay, you can interrupt me for anytime later. And what I want to do now, sorry, yeah? I've heard something.
Okay.
All good.
Yeah.
Oh, good. So I go on. Yeah, so as I anticipated in the outline, I want to start by looking at the static component of the interaction, which means, the static component, that's the first part of the talk. So I take this model and I do the static approximation where I eliminate the cavity, the mode, the mediator, in the static approximation, also called the adiabatic approximation, meaning that the characteristic, the tuning of the cavity or frequency of the cavity that Andreas talked about becomes much larger than all relevant scales in a way that actually I will define more precisely later. And this trivially leads to a coupling which is, again, density, the same density component to the square of the coupling between metal and light, the usual illumination divided by this frequency scale or the tuning delta C. So this is very standard. So let's see what this does. So very naturally, we see that this type of interaction, being a density interaction with this Q naught component, favors the creation of a density modulation with this Q naught, which is this order parameter here, which I call here charge density wave, that is nothing else of the fermionic version of what Andreas just told us, and he called it self-organization transition or superradial transition. And this happens if this effective interaction is attractive on this side, and you go beyond a certain strength of this attractive coupling. And this is also as a function of temperature. It becomes more difficult to do it at higher temperature. So these first thermal experiments were like here, and the ultra-cold experiment are more like here, but is continuously connected. And that's the physics of this charge density wave. And this is the most natural kind of transition that you can have in these systems. And now my question is, okay, these are the experiments. I should tell you that the experiments that Andreas mentioned for bosons are now being done observing this charge density wave or superradiant transition also for fermions. It essentially works the way as very nicely Andreas introduced for me, and all works as expected. But the fact that we have a Fermi surface, of course, adds a few interesting features. I would like to mention one, which I think is very interesting, which is the fact that if you put yourself at the superradiant or charge density wave transition here, and you look at the critical behavior, you see that at the critical point, the fluctuations of the electromagnetic field in the cavity become so strong that they can destroy the electronic or the fermionic quasi-particles around the Fermi surface, leading to this so-called non-Fermi liquid behavior, in this case characterized by a decay or quasi-particle damping that it becomes dominant at low frequency, which is characteristic exponent 2/3. And I think this is the first thing that you can say what changes if you have a Fermi surface. You can look at this kind of quasi-particle properties here, what happens around the Fermi surface. And I should comment that to have actually this the destruction of quasi-particles, you need to go away from the single mode cavity more to a multi-mode cavity like the ones realized in the experiment of Ben Lev Stanford, where you have many modes and you need a continuum of modes to destroy the quasi-particles, but it's the same kind of superradiant or charge density wave transition criticality that makes this possible. But this is like a parenthesis, so let me go back to my single mode case and ask the following question. We experiments even have already seen that this charge density wave exists also for fermions, actually, and my question is, what happens in the rest of the phase diagram? Are other orders that compete with this? And the first observation is that we can take our effective static interaction mediated by the cavity that I wrote in this way and rewrite it back in terms of fermionic creation and destruction operators. And this charge density wave order parameter corresponds to taking this fermion bilinear C dagger C, like in this way I defined before. But actually there are other bilinears that you can take, and you should concentrate, given the fact that we have a very well-defined Q0 transferred by the cavity, we should concentrate on these 4 hotspots on the Fermi surface. These are called hotspots because are the spots, the positions on the Fermi surface that couples most strongly via this interaction, where you expect the leading order effects to happen. And so you can do other combinations. You can go in the pairing channel or the pairing type of ordering, which would correspond for electrons in superconductivity. For fermionic atoms is called superfluidity just. And this corresponds to this bilinear CC and to these leading hotspots across the Fermi surface in the standard Cooper channel minus KK. I'm assuming here spinless fermions for simplicity, which means for ultra-cold atoms like spin polarized cloud. And there are still more competing instabilities. The other one is not the standard Cooper pairing, but it's the pair density wave, which means to take these 2 electrons here on the Fermi surface, and this is a gap function, which is now modulated in space with this characteristic momentum P0, which is not the Q0 of the cavity, but points in the orthogonal direction. This is a possible instability. And yet another one, which it is the other couple of hotspots, but now not with 2 electrons, but with an electron and a hole, which is the formation of an exciton and the corresponding condensation, which is also possible and corresponds to this other bilinear here. So we have all these possible so-called channels that can compete, or ordering phenomena that can compete. And my first observation is the following. You see that the corresponding order parameters for the standard charge density wave that I started from, we have a sum over the whole Fermi surface, sum over K. For the other ones, we don't have this sum, but actually every pair of hotspots on the Fermi surface work differently. I have one order parameter for every K, for every pair of hotspots. This situation where we have one instability or one ordering that come over all the Fermi surface and the others have decoupled pairs of hotspots comes from the fact that we have an infinite range interaction with a finite Q being involved, very sharp structure in momentum space. And the fact that it is this charge density wave that has this sum over the Fermi surface, which can be called collective enhancement, comes from the fact that, as I told you, the interaction is naturally written in the density channel. It's exactly an interaction between these 2, if you want, order parameters. This is why this is the collectively enhanced channels and the other are non-enhanced, which means that if I go on the attractive side of the coupling, where I have the possibility of charge density wave, if I write the phase diagrams using T over TF and G over EF, I actually have the superradiant transition at a coupling which is reduced by a factor 1/n, like is collectively enhanced. To repeat again what I mean more concretely. Therefore, to look for these other three instabilities, I should rather go on the other repulsive side and do they exist also there? And they do. And actually, if you consider them, consider only these four hotspots, only the four hotspots, then they are actually all three degenerate. Exciton condensation, pair density wave, and Cooper pairing, using these four hotspots, are completely degenerate, meaning that they have the same TC. If I go beyond the hotspots at finite t, I find that the Cooper instability or the pair density wave instability, they are still degenerate. The coupling strength that goes linearly, starts linearly with like they have a TC, which starts linearly as a function of the coupling strength, and plus polynomial correction that come from finite t. And the interesting thing is that these instabilities, they exist independent of the sign of the coupling. You see on both sides of this axis, we have these transition lines of the pairing. And this is due to the fact that, again, we have an infinite range interaction which doesn't have the Q equals 0 component. It has the Q naught component. This means that to come back from the Fermi surface, I have to go to, if you want, to second order in perturbation theory, and the thing becomes, you have equations that go like t squared equal to something like g squared, and then we take the square root, you take the modulus, and in the end, you get a sign-independent type of transition line. And the second observation is that the exciton condensation, which is not in the pairing channel, but in the particle hole like type of instability, it has always a lower TC. And this is because it involves particle and not particle and particle. And you need a finite thermal occupation to have this dominate, and it has only just an exponentially small enhancement, and therefore it will always lie below these pairing instabilities. So in the end, the phase diagram looks something like that. On the attractive side, you have this charge density wave or superradiance. In a very small region, you might even have pairing, but if you go on the repulsive side, the pairing should be essentially the only thing you have. And so let's look at how the pairing actually looks like. What is how does this gap function actually look like on the Fermi surface? And that's how it looks like. I'm showing here the gap function in 2 dimensions on the Fermi surface and around it at 2 different temperatures, like corresponding to this cut here. One very close to just below TC, and the other at here t equals 0. And the first thing I want to observe is that here we have the gap function that as first thing is that it changes sign across the center of the Fermi surface, so it has a node. Corresponds, if you want, to p-wave type of pairing, and this is because we are taking spin-polarized fermions, so this spatial part has to be antisymmetric, and the fact that it's still possible on the repulsive side for spin-polarized fermions is because we have this infinite range interaction. And it has yet another sign change, which is in this direction, because it goes from blue to red also in this direction, and this is because the interaction is repulsive. So to have a finite gap, it has to alternate sign if you move by Q naught. In Q space. Final observation, which I think is important, because if I didn't tell you whether this gap is actually Cooper pair or pair density wave, and it actually turns out that only at these 4 hotspots, only at these 4 points into the Cooper pair and pair density wave are degenerate. So they will the fermions at these hotspots will not know whether, let's say, to order in the Cooper or in the pair density wave channel. But if you move away from these hotspots anywhere else on the Fermi surface, like here, this will be Cooper pair winning. So the take-home message is that if you want really a finite, like a relevant part of the electrons or fermions to pair in this more exotic pair density wave, you need to be essentially in 1D. But then the strength of the cavity-mediated interaction makes this at temperature scales accessible. I can tell you more about the parameters if you're interested, but that's basically the main message. So I think I would like now to move to the second part of the talk, to the dynamical part, but I stop again for questions, maybe if I completely said something unclear or something like that.
Can I ask then a question? So you are ignoring any dissipation from the cavity, but I mean, there is always a kappa. So how is it to access these phases?
Yeah, so I will come to kappa now when I do the dynamical part, because it's very important there. For the static part, if you do this type of, if you write the interaction in this static approximation like here, so basically I go back to here where I have this term. Now, if kappa adds, then you will have a delta C in the numerator and delta C squared plus kappa squared in the numerator. And if you're far away, sorry?
There is another jump operator that is proportional to
Yes.
the same term.
But I would say that if the detuning is sufficiently larger than kappa, the static part works in this way. And then you might worry about the dynamic part, which is affected by kappa in a way that I plan to tell you in the next slides. So I would say...
But if you have to do adiabatic preparation that is slow, doesn't hurt you at some point, because in order to reach the ground state. Well,
that's a point that there are the answer to that question is, if I have a single cavity mode, as you're right, the kappa will, the dissipation from the cavity will allow you to redistribute the atoms and actually bring them at long times to a temperature which is of the order of kappa, which is much larger than the ultra-cold temperature that they have. Same for bosons, you know. But the time it takes for this cavity heating or cavity cooling to happen, it's long enough that this is not seen in the experiments with fermions I mentioned in the beginning. So if that's your question. But then kappa affects also the interaction. Even if you don't analyze what kappa does on the redistribution of the atoms in terms of being not thermal anymore or heated up, still it affects the dynamical part of the interaction I want to discuss. So does it answer the question or?
Yes, perfect. Thank you.
Thanks. More questions?
Yeah, the one.
Wait. Can you hear me?
Yes.
What is the ratio between Q naught and K Fermi in your system? Or like, is that also a parameter that you can vary?
You mean KF? Yes. This can be varied in several ways, but I can say that, for instance, in this experiment here, where they have the charge density wave, I remember the value here is like, can be, depending on the type of angle of driving you use, I remember it's something like 0.6 kF.
No, sure, but for what you're presenting, is it at a fixed Q naught, or
it is fixed?
Have you varied?
I mean, I can vary it, but it doesn't change as long as Q naught is finite. And it changes when Q naught becomes so large that you don't have any more these 4 hotspots. You know, when Q naught becomes larger than 2 kF,
yeah,
then you don't have any more this 4 hotspot physics, right? Am I making sense? Like if this Q naught becomes too large, then I don't encounter these hotspots anymore.
But what I'm surprised by is that it doesn't change the competition between PDWs and Cooper pairs. But maybe that's.
I think it will change it in the 2 limits. One limit, as I said, when Q naught exceeds 2 kF, and it will also change it when Q naught becomes so small that you cannot basically resolve these separated 4 hotspots. Let's say if the Q naught becomes smaller in energy terms than the quasi-particle damping or something like that, then you cannot talk about separated hotspots anymore. And then with a hot Fermi surface, it's called this regime, then I don't know the answer yet. But otherwise, it's really, if I have a fixed Q naught, you can really exactly solve in mean field, because it's complete forward scattering, if you want, in the language of solid state, but with a finite Q naught, I can demonstrate that there's nothing beyond mean field in the static part. And then I can really see that they are all degenerate and have this type of scaling of TC. Because it's in the paper we're writing, but the Cooper pair and pair density wave, due to this peculiar structure of the interaction, can be mapped into each other if you have only the 4 hotspots. or only multiples of hotspots? And to complete the answer is the Cooper wins everywhere on the Fermi surface apart from the hotspots, right? So Cooper wins everywhere apart from these 4 points where it is degenerate with pair density wave.
Okay, thank you.
Okay, I shall go to the dynamical part. I guess I have something like 15 minutes.
Yes, you are in 25, yes, that one.
Yeah, yes, with some questions. So dynamical component. So I go back to I have the same model, standing wave, single cavity mode with a given Q naught, but now I introduce back my photon. And I ask, what's the role of going beyond this static approximation that there was questions about? And to do that, to have an approach that includes, if you want, everything, we use, we write an equation not anymore for the Hamiltonian with a limited cavity, but we study the full scattering between two fermions coming in, two fermions coming out. This is called Bethe-Salpeter equation for the vertex function. And this sums an infinite series of scattering process and the quantum mechanical amplitudes. And it boils down to solving an integral equation for this vertex function gamma. When gamma diverges, it means that you have an instability towards the corresponding ordered phase. For those of you that are familiar with solid state, this is equivalent, at least for computing critical temperature, to the usual Eliashberg approach to superconductivity, where historically one used this to study the dynamical component of the phonon-mediated interaction between electrons, which is indeed the relevant thing in standard superconductivity. So this is somewhat equivalent approach. And I will start by making contact with the static approximation that I just finished discussing. And I do it in a simpler limit now when Q naught is much smaller than K. And I will consider only the Cooper pairing that we saw before that at least looked like the dominant instability. And the static interaction, as I told you, is like adiabatic photons or virtual photons, meaning that the characteristic energy of an electron excited by the photon is Vf times Q naught, and this is much smaller than delta C. And in this regime, there is a very well-defined static part of the interaction. And if I formulate the static interaction in terms of this equation for the vertex function, I get this equation where gamma is the vertex function of two electrons wanting to pair being at the Fermi surface. And this equation, you recognize the factors that I used before. And this is the equation that I get for the critical temperature 1 minus 2 g squared over delta C Tc, and g squared over delta C was our GF from the slides before. And apart from a factor of 2 that I have to apologize about, which is a different notation between the two parts, I'm sorry, but apart from that, it's the same critical temperature we saw for the Cooper pairing at leading order in the static approximation. So let's say the static approximation means only considering scattering processes where the electrons or the fermions, by exchanging a photon, stay in the vicinity of the Fermi surface. But always, there is another component, dynamical component, where these electrons exchange a photon, but not a virtual photon, but a real photon. A photon excited at its own characteristic frequency or energy delta C, which is the energy of this cavity mode. And this, of course, if delta C is much larger than VFQ naught, brings the electron or the fermion far away from the Fermi surface on this shell. And in order for it, let's say, to pair, to give rise to this instability of the Fermi surface, it has to be scattered back by a second photon back to the Fermi surface. If I introduce these extra processes in this equation for the vertex function, I get this additional term. This additional term is proportional to the density of photon, which it makes sense because I'm considering absorption and emission of real photons now, not anymore virtual photons. It has this scaling again with g squared over delta C squared, which is our like small dimensionless coupling constant. And it has one thing which I find very interesting coming from a field where you want to mix quantum optics with condensed matter physics, which is you have a cooperativity appearing here. People from working with cavities are very familiar with this. And this cooperativity is the cooperativity that involves, again, cooperativity always has the coupling square in the numerator, and in the denominator you have the dissipative processes that work against this type of scattering process. And on the one hand, you have the lifetime of inverse lifetime of the photon, so the width of the cavity that Anna Maria asked about, and then also the width of the electrons, so the inverse quasi-particle lifetime of the electrons. And now, if you want, you can think about this being processes that scatter back and forth from the Fermi surface, a kind of two-level atom for every K on the Fermi surface. But in order for these scattering processes which involve real photons to be relevant, you have to have a high cooperativity of these transitions. And this means that the ratio of d square over the dissipative process, meaning the width of both levels, being one, the Fermi surface determined by the quasi-particle lifetime, and the other level, or before the photon lifetime, is like kappa. So let's say you have a cooperativity appearing in an equation for a pairing instability because that the cavity has a resonance, and scattering processes between electrons or fermions can happen by exchanging real photons. If I consider now the effect of this on Tc, I can solve this, and in this plot I can find Tc using, for instance, the Fermi liquid lifetime of electrons at finite temperatures here, and I find that compared to the BCS prediction, so the static approximation, if I have a finite number of photons, I can increase Tc by putting more photons into the cavity by a lot, by even order of magnitude, by having here, I guess, this value corresponds to I guess, 3.2 photons, I'm not sure, but the point is that the Tc, as a function of the pump, if you, let's say, imagine pumping incoherent photons into the cavity, as a function of the pump strength, the Tc grows linearly. So it seems that you can really inject photons to mediate stronger interactions, which is clear from this. But you know, using here, I guess we used a realistic parameter for a solid, not for ultra-cold atoms. But for ultra-cold atoms, this formula will work in the same way. Just you have a different lifetime because it will not be, well, depending on whether they are interacting or not. But in general, the lifetime is different between electrons and ultra-cold atoms. But the message is these resonant processes make you allow you to increase the critical temperatures by a lot by injecting more photons. So this is the first, or the second, if you want, peculiarity of the cavity-mediated interaction, that due to the fact that the cavity has a well-defined energy, the photon in the cavity has a well-defined energy and momentum and can be injected controlledly, you can make this dynamical component in terms of resonant processes very, very important and use it to enhance the collective phenomenon. And I guess in the final 5 minutes, do I have 5 minutes?
Yes, kind of 3, and then 5 for questions.
Yes. So now we've seen, one last comment on this resonant process. We've seen that these processes involving absorption emission of real photons, these resonant processes, they depend on the number of photons. So in general, they depend on the quantum state of the photon, quantum state of the light in the cavity. So one can ask the question, what happens if instead of putting incoherent photons or thermal photons, I put really more non-classical states of light? And well, you need to further generalize this vertex equation to being able to include this feature. But the first message I want to give is that if you do this, as soon as you have a non-Gaussian state of the mediator, so not a thermal state, not an incoherent state, but if you have a non-Gaussian state, you have an additional structure emerging for this equation for the vertex that reflects the Hilbert space of the mediator, in this case, the photons. And in this case, the Hilbert space is the Fock space, most naturally. This is the equation for photon put in a pure Fock state. And this emergent structure can be solved iteratively in a way that I can tell you about if you're interested, but let me jump to the result, is the fact that not only by playing around with the quantum state of photons between like a thermal and a Fock state, you can change Tc by a lot, but you can even change the most difficult thing to change, which is the critical exponent, the susceptibility of exponent of the superconducting or superfluid transition generated by this pairing instability. For a thermal photon state or vacuum state, you have a susceptibility exponent, which is the BCS exponent gamma equal 1. But if you have a pure Fock state, let's say, with more than you want one photon, let's say 2, you get gamma equal 3. And in general, you can show that the exponent is equal to n0 number of photons in the Fock state plus 1. If you take a Fock state and you say in experiment you can never inject Fock state, you don't have pure Fock state sources, but you have very good Fock state sources. So let's broaden it a bit with a factor kappa. And you see that if you have appreciable broadening, but not very large, which correspond actually in this scale for kappa large. So kappa in my scale is the inverse of the broadening now. So sorry for the mess in the notation, but this kappa is not the broadening, the inverse broadening of the cavity line width, but is like the broadening in terms of Hilbert space, the inverse broadening in Hilbert space. But the message is that you can have few decades where the critical exponent of a pure Fock state, and if you get arbitrarily close to the transition point, then you see that you don't have a perfect Fock state and you switch back to the gamma 1 BCS exponent. So with this, I think I want to flash the summary slide, and thank you for your attention, and I hope there are more questions. Thanks a lot.
Perfect. Thank you. So we are open for questions. In the back, yeah.
If you take your resonance to 0, like if you're like in the last equations, can you like arbitrarily increase TC in your?
You mean the cavity line width here?
Yeah. No, delta C. Delta C.
The tuning.
The tuning.
Ah. No, no, because all my calculations work in this kind of perturbative regime where G square is much smaller than delta C squared. Like this is a small parameter. And this is, are you familiar, if you're a equation for phonons, this is also called weak coupling there. Because if you go in strong coupling, where the coupling between phonons and electrons becomes comparable to the characteristic phonon energies, then you go in this strong coupling regime where things change completely. And you have to solve this stuff numerically, these integral equations numerically. And I don't have an analytic answer there.
Right, more questions?
Thanks for the nice talk. Just wanted to ask, in the first part, in the static part, the results you showed were for electrons or for fermionic atoms, or for both?
I would say for both, if with a bit of optimism. Let's say the reason is the following. Let me go to the slide. In terms of model, so the first difference is that electrons normally don't couple to the density, right? The photons don't couple to the electron density, but to the electron current. To make this model where I couple fermion density to photons, to make it solid, I need to use laser dressing. But this is in principle possible. People put serious numbers and you can do it. So in principle, this model is valid for both. This is why I call it light matter and not atom photon. What is very unnatural, however, in solids, is that we have a Q0, which is an appreciable fraction of Kf. Because the wavelength of an optical cavity cannot resolve the lattice spacing in a solid. And therefore, Q0 will be much larger than Kf in a solid, which means that some interesting competition might happen, but you will not have these very well separated hotspots. So I cannot give you, so the answer about competition will be still interesting, I think, but not that simple.
But so if you say that it's for both, I'm just wondering then, I mean, how does this phase transition that we would see, this you predict it also for electrons? There are, all of these no-go theorems which they prevent from having this phase transition for electrons because of the diamagnetic interaction.
Yes, but these no-go theorems apply not to this coupling that I'm using. The no-go theorems apply to this coupling, to the current. And I know these no-go theorems, they apply if you consider electrons current coupled to the photons, because this is the gauge theory then, and the diamagnetic coupling, you need to maintain gauge invariance. And if you violate gauge invariance, you get a transition. If you restore it, you don't get it. But it turns out that the charge density wave transition, what I call charge density wave transition, if you look at it for these models, when you couple to the current, those are states where you have a finite current of electrons and a finite number of photons. And there is no good theorems for the Q equals 0 version of it, but there are now several papers showing that it is possible for finite Q there too. So the no-go theorem doesn't hold even in solid state to look at finite Q superradians.
Okay, thanks.
Maybe, I mean, like related to the question that Vasilis just asked, like, can you say a bit more about the realistic parameters in experiment? So like at some point you said that G has to be 60% of the Fermi energy. Is that realistic in experiments? And then like further later on, you said that G has to be smaller than delta. So like, how does this really, like in some other experimental platforms that realize this parameter? Yeah.
So if you talk about the first part about the static competition, we took exactly the parameters that are valid for ultra cold atomic experiments with Fermi. So we took really the numbers from the experiments in the PFL that I cited in the beginning. So there they have a cavity at an angle with the trapping of the clouds such that the Q naught is 0.6 kF. So it's really perfectly in this regime. The delta C is like something like at least 10 or 100 megahertz. Kappa is several kilohertz. So it's really in the regime we consider. And the G can be tuned and is never as large as delta C, but is appreciable such that you can reach, let's say, this pairing. And the relevant question that you might be in the end asking is, let's go on the repulsive side where I don't have to fight with the charge entry wave, which has been already seen. And what is the T that the pairing on this side, given the maximal GF that experiment can reach? And for that, we put the numbers, and you are very well with reasonable effective couplings that you can reach in this experiment at the PFL. You find that TC for the pairing, which is of the order, can be like 0.1 TF or 0.5 TF, which is the temperature they already have now. So if that answer, this answer is for ultra cold atoms. For solids, I can give you a quantitative answer, not quantitative for solids, like but I can give you a calculation we did for realistic parameter for solids, but this we did only for the Q equals 0 case where we didn't solve the competition, but we just looked at pairing, and this is what I showed you in the last part, where I showed you this increase in TC. But for ultra cold atoms, we really have if you want, no fitting parameters, so I'm more confident in putting numbers.
Thanks.
A very short question. So for the adiabatic elimination, you need G square root of n. Yes, it's not only G. Delta C has to be is G square root of n, no, because of the collective behavior for the adiabatic elimination.
For the adiabatic, you mean for this part, for this to be valid? Well, in the
for when you adiabatically eliminate the photons, you have to have G.
Your square root of n, you mean the square root of of atoms?
Yes. Because it's collective, so you have to have this term smaller than the energy of creating and absorbing a photon. But okay, we can. Might be.
I need to review my calculation, but I can believe what you say. Yes. Yes, but you know, it's still the experiment is easy to enlarge delta C. It's difficult to make it below kappa. Yeah.
Yes. Okay, great. Okay, I think we are.